Recording. All right. Yeah, so Professor Ferrante already gave you the title, and this is all work that we've done together over the last 5 or so years. So I'd like to begin just by giving some acknowledgements. First, of course, thank you to Professor Ferrante for being so patient with me over the last few years, especially as I figured out how to do fluids research with really only a math background. And thank you also to the rest of my committee, Chris Brotherton, Jim Riley, and Alberto Aliceta. Your comments at my general exam were extremely helpful. I also really appreciate your being able to fit this exam into your busy schedules with such short notice. Thank you also to the Department of Applied Math. The faculty, staff, and students have been really supportive. Thanks also to my friends here in Seattle who made the last 6 years really fly by. And of course, to my family as well for being huge supporters in my education. So the main topic of this talk will be droplet-laden turbulence. Turbulence is just chaotic pressure and velocity fluctuations in fluid, and droplet-laden turbulence is turbulence that has droplets in it. The physical mechanisms of the interaction between droplets and turbulence are largely unknown. It's a difficult kind of flow to simulate or to extract data from in simulations. So we're interested in improving this understanding. Droplet-laden turbulence has a number of different applications in engineering and nature. So just a couple of quick examples. One would be spray combustion, like you might find in the engine in your car. And then another timely application would be transmission of respiratory droplets, for example, droplets containing the coronavirus. So our main tool in studying turbulence is direct numerical simulation, or DNS. So turbulence is a very multi-scale phenomenon that has very large and very small scales occurring at once, which means that simulating turbulence requires a lot of computational power. And DNS basically just solves the governing equations across all of the scales using very fine grids and doesn't do any kind of modeling. But hopefully through DNS and gaining a physical understanding of droplet-laden turbulence and gaining data from DNS, we'll be able to create models to make simulating these kinds of flows easier. So in the introduction, I'll begin with some recent work. So this was work done by Michael Dodd, who was the last PhD student to graduate from this group. And he and Professor Ferrante published a paper in Journal of Fluid Mechanics in 2016, where they performed DNS of decaying droplet-laden homogeneous isotropic turbulence on a 1024 cube grid. So decaying turbulence means that no energy is added to the flow after it begins. It's just allowed to decay naturally as energy is lost through dissipation at the smallest scales. Homogeneous and isotropic mean that the flow is statistically invariant to translation and rotation. So the boundary conditions are all periodic, and this is kind of an idealized flow without gravity that lets us really focus on the effects that the droplets have on turbulence. So on the left here is a snapshot of one of the simulations from this paper. So in white, you can see the surfaces of the droplets, and in red are some of the vortical structures present in the flow. And the table on the right shows some of the main flow parameters in the study. So in all the cases, there were 3,130 droplets, which made up 5% of the domain. And the droplets are initialized spherically with an initial diameter of 32 grid cells. The Reynolds number, which is the ratio of inertial to viscous effects in the flow, and also the main non-dimensional number used to classify turbulence is 83. So the flow is fully turbulent, although it's on the low scale of Reynolds number. And then there are 3 parameters that are varied between the 7 droplet-laden cases in the study. The first being Weber number, which is the ratio of inertial to surface tension effects. And so lower Weber number means more surface tension essentially, and that's varied between 0.1 and 5. And then also the ratio of droplet density to carrier fluid density is varied between 1 and 100, as is the ratio of droplet fluid viscosity to carrier fluid viscosity. And so in this paper, Dodd and Ferrante analyzed spatial statistics of the flow and derived balance equations that explained how turbulence kinetic energy, or TKE, is transferred between the carrier and droplet fluids. So here are the governing equations that we'll be dealing with primarily. So these are the 2-phase incompressible Navier-Stokes equations, which should look just like the single-phase Navier-Stokes equations that you're familiar with. We have the mass conservation equation, as well as a momentum conservation equation with the addition of a extra term F sigma at the end, which accounts for force per unit volume due to surface tension. And then the other difference with the 2-phase equations compared to single phase is that density rho and viscosity mu are now piecewise constant because they are allowed to vary between the 2 fluids. U sub I is velocity in the ith direction, and P is pressure. And we're using Einstein notation here, so the repeated indices imply summation. And then here's a quick summary of the numerical method used for this DNS study. The droplets are tracked using a volume of fluid method, or VOF method. So there's a VOF function chi, which is defined to be equal to the fraction of the grid cell occupied by a droplet. So in the carrier fluid where there's no droplet fluid in the grid cell, chi would be equal to 0. And inside the droplet, chi would be equal to 1. And then if you're looking at a grid cell that's occupied by part of a droplet, so along the interface, chi would be somewhere between 0 and 1. And it's governed by an advection equation. So the VOF method involves taking the VOF function and using that to reconstruct the normal vector to the interface, locating the interface within a grid cell, and then advecting chi appropriately. Then the Navier-Stokes equations are solved using a pressure correction method. In particular, one called FastP star that was also developed by Dodd and Ferrante. And the advantage of FastP star is that it results in a constant coefficient Poisson equation for pressure. So in a pressure correction method for a single phase flow, you would also have a constant coefficient Poisson equation, which would let you take advantage of a fast Poisson solver that uses the fast Fourier transform. But normally in multi-phase flow, where the density is allowed to vary between multiple fluids, you would have a variable coefficient Poisson equation that would require using something more expensive like multi-grid, for example, to solve. But FastP star lets you use a fast Poisson solver because the Poisson equation is, again, constant coefficient. And then lastly, for our introduction, I'll go over the objectives we have. So the original goal was to develop a better understanding of the energy spectrum for droplet-laden isotropic turbulence and how it varies when we change these 3 parameters, Weber number and density and viscosity ratios. And this is research that we published in the Journal of Fluid Mechanics last year. It'll be the focus of the first half of the talk. And if you were at my general exam last year, some of this might seem familiar. And then the second half of the talk will deal with using the results from the first half to create new models for large eddy simulation of droplet-laden turbulence. So in the second half, we'll talk about how we implemented a model and show results. All right, so like I said, we want to use the energy spectrum to get a better understanding of droplet-laden turbulence. The energy spectrum is a tool that's often used in studying turbulence, and I've given the definition here. You take the Fourier transform of the velocity fields and square their magnitudes at each wave number, essentially. So this gives you information about how much energy is contained at different scales of the flow. And like I said, turbulence is a multi-scale phenomenon, so you end up gaining a lot of insight by seeing at which scales the energy is contained and how energy is transferred between scales. And the turbulence has a phenomenon called the energy cascade, in which energy is transferred from the larger scales to the smaller scales and eventually lost to dissipation at the smallest scales. So in the paper by Dodd Ferrante, they published the energy spectra for the 7 droplet-laden cases, which are shown by the colored solid lines in this plot, as well as 2 droplet-free cases, which are shown by the dashed lines. And we can see a few noticeable differences between the droplet-laden and droplet-free spectra. So first, at the large scales, or at the low wave numbers, energy is decreased in the droplet-laden cases compared to the droplet-free cases. At the high wave numbers, or small scales, energy is increased. And at these high wave numbers, we can also start to see some oscillations appearing in some of the droplet-laden spectra. I just want to point out that these observations alone don't necessarily increase physical understanding of the flow. And indeed, these spectra were included in the paper at the request of a referee, not necessarily because they provided any physical insights. So we wanted to find an alternative to using the Fourier spectrum, so because the Fourier spectrum we saw has a couple of disadvantages. One is that in multi-phase flows, we typically have sharp changes in velocity near the interface. So in the plot down here, I've shown velocity along a line in the domain for case A, which was a droplet-free case, and then also case C, which was one of the droplet-laden cases. And the shaded areas show when case C passes through a droplet. You can see at the edges of the droplet, the velocity shows pretty sharp changes. And so since the Fourier spectrum uses the Fourier transform to be computed, and the Fourier transform can't handle these sharp changes very well, we end up with these oscillations at the small scales, as well as the increased energy there. And furthermore, with the Fourier spectrum, once you apply it, you lose all of your spatial information, which makes decomposing the spectrum difficult. So we wanted to find a solution that would let us look at specifically the spectrum of the carrier fluid and see how that's affected by the droplets. So we decided to turn to the wavelet spectrum, which uses the wavelet transform to be computed as opposed to the Fourier transform. And its advantages are that it handles non-smoothness better, and also it preserves spatial information. So the discrete wavelet transform is similar to the discrete Fourier transform, but whereas the Fourier transform will represent a function in a basis of sinusoidal functions with different frequencies, the wavelet transform will represent a function in a basis of these wavelet functions, which are not only different, or they're dilated, so they're stretched, but they're also translated. So you can see here 2 examples of different wavelet functions. And they have compact support, so they're non-zero only on a bounded set of points, which means that when you take the wavelet transform, not only do you get information about the frequency of the signal, but you also get information about the frequency of the signal at certain points in the domain. In our study, we chose to use the SIM4 wavelet, which is the one shown on the right here. The wavelet spectrum is defined in this way. It's analogous to the definition of the Fourier spectrum. So the W sub I are wavelet coefficients of the velocity in the ith direction. And to get the wavelet spectrum, we square these, just as we squared the Fourier coefficients. However, now the wavelet coefficients are also dependent on this index L, which is an index over the points in space at which the coefficients are defined. So once we square these coefficients, we also average in space. The factor out in front just scales the spectrum to be per unit wave number, and the wave number is defined in a similar way as the wave number for the Fourier spectrum. And M here is the scale of the wavelet, so larger M means smaller wave number. And once we have the definition of the wavelet spectrum, we can also derive a wavelet spectrum evolution equation, which tells us the rate of change of the spectrum in terms of these three terms. T represents the energy transfer rate due to convection and pressure, V the viscous dissipation rate, and then S the energy transfer rate due to surface tension. And so, as we mentioned earlier, our goal was to be able to decompose the spectrum. So our decomposition for the domain involves three parts, the carrier part, the droplet part, and then what's left over, which we call the interaction part. So to determine whether a point in the domain belongs to a carrier fluid, first we pick a wavelet scale M, and then we look at all the points at which the wavelet coefficients at scale M are defined. And then we look at the width of the wavelet at those points for the given scale. And if the wavelet extends, or rather doesn't extend into a droplet, then we put it in the carrier part of the domain. If the point is in a droplet, is in the droplet fluid, and the wavelet doesn't extend outside of the droplet, then that point is in the droplet part of the domain. And if the wavelet centered at a given point crosses between the carrier fluid and the droplet, then we put it in the interaction part. And so by selectively averaging over these three parts of the domain, we can define three different spectra, the carrier spectrum, the droplet spectrum, and the interaction spectrum. So here is a plot showing what the decomposition looks like for the two highest wave numbers in case C. I suffer from mild color blindness, so I'm about to embarrass myself here potentially, but I think so the yellow is the carrier part of the domain, the pink is the interaction part, and the blue is the droplet part. And in the highest wave number, so this is the smallest scales, we see pretty good resolution between the three parts in decomposition. As we move up in scale to the next lowest wave number, we see that there are fewer points where we can define the carrier part of the domain, because the wavelet coefficients are defined at fewer points and they're also wider. So there's not as many spots in the domain where we can fit a wavelet that doesn't cross into the droplets. So in fact, once we go down to any of the wave numbers below 128, we can't really decompose the domain anymore because the wavelets become too wide and the droplets are too close together. We apply this decomposition both to the spectra and to the terms in the evolution equation. So now on to the results. So we're splitting the results up into three groups, or the cases rather. In the first plot, we show the cases where we vary the Weber number between 0.1 and 5. In the second group of plots, we vary the density ratio between 1 and 100. And then the last plot, we vary the viscosity ratio between 1 and 100. And in all these cases, case A, which is the baseline case without any droplets, is shown in black. So we're going to show three main results. First, that the droplets do not affect carrier energy at high wave numbers. Second, that the droplets increase interaction energy at high wave numbers. And third, that the droplets decrease energy at low wave numbers. So for the first result, we want to look at the carrier wavelet spectra. So like I mentioned, this is defined at the three highest wave numbers. And we see that the droplet-laden cases overlap almost perfectly with the droplet-free case. So this tells us that at these high wave numbers, or small scales of the flow, the droplets have almost no effect on the carrier fluid energy. To be sure, we can also look at the terms in the evolution equation for the carrier spectrum. So the two terms are first, the spectral energy transfer rate due to convection and pressure. And we see again at these high wave numbers, there's very little change between the droplet-laden cases and the droplet-free case. And then we can also look at the spectral viscous dissipation rate at these wave numbers. Again, very little change when we introduce the droplets. So again, this shows us that introducing the droplets really has little effect on the energy content at small scales away from the droplets. For the second result, we look back now at the total energy spectra. So as with the Fourier spectra, we notice that at these high wave numbers, there's also an increase in energy. And we just showed that that increase is not due to the carrier part of the decomposition. So now we look at the interaction part, which again is the part of the decomposition where the wavelets cross the interface. And we show that when we look at the interaction spectra, this confirms that the increase in energy is due to this part of the decomposition, namely the area near the interface. And we found that this increase is due to the sharper gradients. So as we saw with the Fourier spectra, there's high velocity gradients at the interface, and this is due to varying either one of these or any one of these parameters. So if we decrease Weber number, the droplets become less deformable. If we increase density ratio, the droplets gain inertia. And if we increase the viscosity ratio, we also end up with sharper velocity gradients. So again, by varying any of these parameters, we increase the velocity gradients at the interface, and that increases the interaction energy spectra, which increases the overall spectrum at these wave numbers. Then lastly, looking again at the total wavelet spectra, we see a decrease in energy at low wave numbers in all of the droplet-laden cases except for case E, which is the case in which the droplets and carrier fluid share the same density. To see why this is, we look at the viscous dissipation rate term of the evolution equation. We see that viscous dissipation is greatly increased at these low wave numbers in all of the droplet-laden cases, except for, again, case E, where the density ratio is equal to 1. So this tells us that the inertia of the non-buoyant droplets disturbs large-scale eddies by being resistant to carrier flow motion. And that's what takes energy out of the large scales of the spectrum in the case of droplet-laden flows. This schematic just shows kind of a visual summary of these results. So away from the droplet and the carrier fluid, we have these small scales that are unaffected by the presence of the droplet. Around the droplet interface, we have increased velocity gradients, and these also increase the local dissipation around the droplet. And then at large scales, the droplet causes an increase in dissipation and reduces energy. So that was it for the wavelet analysis. So we'll turn now to the second half of the talk, which deals with large eddy simulation. So again, I mentioned earlier that direct numerical simulation, or DNS, is very expensive because it has to resolve all of these fine scales of turbulence. So one of the main alternatives is you just run a simulation on a much coarser grid, and then by doing so, you leave some of the scales of turbulence unresolved, the scales that are smaller than your grid size. And these effects are called subgrid-scale or SGS effects. And in large eddy simulation, you introduce some kind of modeling that takes into account the effects that you're not resolving. So LES is an important tool because DNS just is too expensive and not tractable for a number of problems, especially in engineering, where you might have more complicated geometries, or in cases where the Reynolds number is a lot higher. So from the results from our wavelet analysis, since we showed that small scale energy of the carrier fluid isn't affected by the droplets compared to single phase flow, we proposed that we could form an LES model for droplet-laden turbulence in which we use a standard single phase LES model in the carrier fluid. And then that would mean that we would only need to create new models for the subgrid scale effects near the interface. And we were inspired by other recent machine learning approaches to LES. So the new SGS terms that will be introduced at the interface, we will model using artificial neural networks, or ANNs. So our mixed LES model, which we call mixed ANN or MANN LES, will use a standard single phase stress model in the carrier fluid. So we chose Smagorinsky SGS stress model here, which is a very classical standard subgrid scale stress model. And then we'll use predictions given to us by our ANNs at the interface. And here's another schematic summarizing this approach. So using the information we gained from the wavelet analysis, we are forming this new LES model where all of these white grid cells here are in the carrier fluid, where we'll just use the single phase Smagorinsky SGS stress model. And then these green cells that occupy part of the interface will use the neural network predictions. So to figure out what the SGS effects that we need to model are, we'll derive LES equations, which we do by filtering the governing equations. So the filtering operation is denoted by an overbar, and then it's defined as just a convolution of a function with another filter function. And the filter that we choose to use is the uniform filter, which is really just, you can think of as a spatial average of nearby points. And so by averaging nearby points, you filter out small scale effects. The filter size we use is 8 times the DNS grid size or grid cell size. So since the DNS grid was 1024 cubed, that means that the LES grid will be coarsened by a factor of 8 in every dimension. So LES grid is only 128 cubed. And that means that the initial droplet diameter will now only be 4 grid cells. So obviously the droplets are fairly poorly resolved now, but the benefit is that we have fewer than 0.2% of the number of grid cells we had in the DNS. So the gains in terms of the reduction of computational resources are significant. And so with this filter size, the subgrid scale effects should be restricted only to cells containing the interface. So again, the neural network predictions will only be done on cells with the interface, and then in all the other cells in the carrier fluid, we'll just use the Smagorinsky model. So filtering the two-phase incompressible Navier-Stokes equations gives us this. So the first 2 lines really look the same as the governing equations that I showed in the introduction, except now all of the flow variables are replaced by their filtered counterparts. However, in the momentum equation, we also now have these 4 additional closure terms. So there's one that comes from the convective term, one from acceleration, one from viscous dissipation, and one from surface tension. The Voff advection equation also gets filtered, so that gives us the 5th closure term. We performed an a priori analysis using filtered DNS data and computed what these 5 terms should be exactly, and found that they're all statistically significant. So we can't neglect any of these terms. We have to model all of them in order to be able to find an accurate LES model. In the following, we'll be focusing on case C from the Dodd Ferrante paper. So this is the case in which the Weber number is 1 and the density and viscosity ratios are equal to 10. So except for the convective closure term, all of the closure terms are 0 in the carrier fluid and in the droplet fluid, because in the case of the acceleration term, rho is constant, so it can be pulled out and you end up with 0. For the viscosity closure term, mu is constant, so you can pull it out, it becomes 0. And then the surface tension and Voff terms are 0 because the surface tension is not defined in the outside of the interface, and the Voff function is constant there as well. So then the convective term we can split up into 2 cases depending on whether we're at the interface or not. And then if we're not at the interface, the convective term is just equal to rho bar times the standard SGS stress for single phase flow. So this is all just to say that because the terms are all 0 away from the interface except for the convective term, those terms we don't need a model. And then the convective term, which is non-zero away from the interface, we will model using the Smagorinsky SGS stress model, like we mentioned earlier. And then now it's time for the everyone's favorite neural network diagram, which is a staple in any machine learning talk. So we're using regression ANNs because we are predicting numerical values for the closure terms, and the neural networks we're using just have densely connected layers. So we're not using any more advanced neural network architectures. The basic setup of a neural network is that there's an input layer, some number of hidden layers, and then also an output layer. The inputs we call features, and the goal of the neural network is, given a set of features, it needs to predict the correct output, which is sometimes called the label associated with the features. And so the neurons in the hidden layer take as inputs the outputs of the previous layer. Then they apply a transformation to them by multiplying them by some weight coefficients and adding a bias B, and then passing that through a function called an activation function. And then that output is then given to the next set of neurons in the next hidden layer. So the neural network will get trained using a bunch of data where we know the correct labels associated with the features, and then the training process will optimize the weight coefficients and the biases at every neuron to try to reduce the error in the predictions and give us the correct outputs that we want. So the training labels that we're using are the values for the exact closure terms that we computed using filtered DNS data. And we're using data from time 1 to 3 at intervals of 0.25. So we start at 1 because that's actually the time at which the droplets are injected into the flow. And we end at 3 because we want to see if the neural networks are able to generalize to later times, even though they haven't seen data from there. And then for each label, the features associated with the label will be the flow variables at the neighboring points on the course grid. So the flow variables will just be the 3 velocities and then also the VOF function. So the goal of the neural network is we gave it training labels that were computed exactly, but then we have features that are taken from the coarser grid, and the goal of the neural network is to be able to kind of interpolate what the closure term should be using only the coarse grid data. So the first table on the right shows some of the parameters of our neural networks. The number of inputs varies because we only take the flow variables that the closure terms are dependent on. So for example, the convective closure term depends on all 3 velocity fields and the VOF function. So that gives us 4 different variables, and we have 27 points for each of them because we take each of the neighboring points on the grid. So that's a total of 108 inputs. For all the neural networks, we used just 4 hidden layers. We experimented with using deeper ANNs, but we didn't really see an improvement in the convergence results. But we did use fairly wide layer widths, so we used 128 ohm, except for the surface tension closure term, for which we used a layer width that was twice as wide. In the bottom table, we show the convergence metrics. So loss is just another word for the mean squared error, in this case, of the test set data. So this is all from points in the inner data set that wasn't seen during training. So loss near 0 is good, and we do have fairly low loss values. And then the correlation should be near 1 for perfect results. And we see that even with the layer width that was twice as wide for the surface tension term, it still struggled the most, which is probably due to the fact that it depends on curvature, which is a second derivative, whereas the other terms only depend on first derivatives. And here we show a scatter plot of exact values for the convective term against the values predicted by the neural network. So anything that's along the red line indicates a perfect prediction. And the orange region is one standard deviation above and below the mean error. So actually, about 85% of these dots lie within the shaded region, but since most of them are near zero, you only really see the outliers here. The numerical method that we're using is still the same VOF function with fast P star pressure correction, like we mentioned in the introduction. The only difference now is that at each time step, we take the appropriate features as inputs for the neural networks, and then the neural networks give back their closure term predictions at the interface. And then one last step we take is we apply a limiter to the neural network predictions. We found that without using a limiter, sometimes the errors would accumulate because the neural networks would introduce some error, change the velocity, and then the velocity would get fed back to the neural networks and eventually cause an overflow. So we don't want that to happen. So the limiter compares the new velocity, including the closure terms, and compares it against the new velocity, what the new velocity would be if all the closure terms were zero. So it enforces that the new velocity with the closure terms should be the same sign as without. So that's kind of like a lower bound. And then the upper bound is that the new velocity shouldn't be more than 1 plus L times what the new velocity would be without the closure terms. So that's like an upper bound that keeps the velocity magnitude from growing too much. And so now we can talk about the results for our mixed ANN LES method for droplet-laden turbulence. So in the results, I'll show 4 different cases. The first case with the blue circles is filter DNS. So this is what we consider to be the exact result, and it's what we want our LES results to match. In the orange with the pluses is a simulation done on the coarse LES grid, but we don't include any of the LES closure terms. In green with the X's is LES with only the Smagorinsky SGS stress term applied across the entire domain. So the interfacial closure terms are not taken into account. And then in red with the stars is our MANN LES method, which uses Smagorinsky SGS stress in the carrier fluid and the neural network predictions at the interface. So the first result we look at is filtered velocity TKE. So we take the square of the velocity across the entire domain and average, and then see how that decays as time goes on. We know that from our DNS analysis that the droplets increase dissipation near the interface, which ends up causing TKE to decay at a faster rate than, or at a higher rate than in single phase turbulence. So first looking at the no LES model case, TKE decays much too slowly. When we add the Smagorinsky SGS stress term, TKE decays slightly faster at the beginning of the simulation, but by the end diverges as much as using no LES model at all. So it tells us that the interfacial closure terms are necessary to be accurately predicted in order to get good results. And lastly, our method performs quite well. It matches the DNS results almost perfectly until time 3. So that was the time over which we gathered training data for the neural networks. And then after time 3, the MANN LES diverges only slightly, which tells us that the neural networks can generalize to future time steps that weren't used in the in the training process. We can also look at the distribution of filtered velocity kinetic energy. So this is the same as the TKE on the last slide, except instead of averaging over the domain, we look at the probability density function. So it's actually difficult to see, but our method overlaps the filter DNS results. So this tells us that not only does our method produce the right average energy across the domain, but it also achieves the correct distribution of energy across the domain. In this slide, we look at the error in the local kinetic energy between the LES cases and the DNS case. So we've kind of skewed the scale here to point out the places with highest error. So in the no LES model and Smagorinsky LES cases, you're going to see a few areas in black which indicate high error in kinetic energy. And the energy is reduced quite a bit in the MANN LES case, where we don't have as many dark black regions. And then we also show positions of the droplets. So in red are the droplets in the DNS, and then in blue are the droplets in the LES. And this is probably the area in which all three of the LES models fail the most. One reason for that is that in the case of LES, since the grid is 8 times as coarse, that means that now the maximum distance the two droplets can get within one another before coalescing is 8 times as great. So droplets ended up joining much more in the LES cases, just because they can't get as close to each other while retaining some grid cells between them. And that ends up meaning that the individual droplets don't get tracked very accurately. We can also look at the energy spectra, just as we did in the first half of the talk. So again, our method ends up matching the DNS results quite well, especially at low wave numbers. And if we look at the error between that for the energy spectra between LES and DNS cases, at low wave numbers, which are the wave numbers in which the vast majority of energy is contained, we have much improved error compared to the other LES cases. We can also look at the terms in the wavelet spectrum evolution equation. So again, we look at the viscous dissipation rate, which is improved somewhat by our MANN LES model at low wave numbers. So we saw with the wavelet analysis that the introduction of the droplets disturbs large-scale eddies. And it shows that this effect is matched better by the MANN LES model as opposed to the other two LES models. And the last result I wanted to show is the TKE and then also PDF of kinetic energy in case D of the Dodd Ferrante paper. So in case D, Weber number was bumped up to 5, so the droplets are now more deformable. And we use the same neural networks as we did for the case C. So this shows that although the results aren't as good as with case C, the neural networks are still able to generalize fairly well to a flow that had parameters that it hadn't seen before. So there are 3 main benefits of our method in our eyes. The first is that it's easy to implement. We just used our existing Navier-Stokes solver, and the only changes we really had to make was to add the closure term predictions. So the Smagorinsky closure term is computed explicitly, and then the neural networks are predicted. The trickiest thing was getting our Fortran code to link with TensorFlow, but that wasn't too bad. And then the neural networks themselves use a pretty simple architecture, just densely connected layers. It would be interesting to try something more advanced like convolutional neural networks, which could be beneficial since our data is structured. That would also require some thinking more about how data is transferred between the simulation and TensorFlow. The method's also easily adaptable. It would be trivial to switch out a different carrier fluid SGS stress model to use besides Smagorinsky, and it wouldn't require retraining the neural networks either. And furthermore, we think that this method or a similar method could be used for other multi-phase flows in which the subgrid-scale stress in the carrier fluid could be approximated by a single phase stress model. And lastly, our method performs well. It was able to closely match kinetic energy of our filtered DNS case, and it also performed well on other cases. So we showed case D with higher Weber number, but we also tested it on case B, which has lower Weber number, and achieved similarly successful results. So in conclusion, I'll just quickly recap the wavelet analysis results again. From the DNS data, we showed that the droplets don't affect carrier energy at high wave numbers. They increase interaction energy at high wave numbers, and they decrease energy at low wave numbers. And we were the first to apply this kind of wavelet analysis to multi-phase flow and use it to increase physical understanding of droplet-laden turbulence, which we then used to guide us in designing a new LES model. So we first performed an a priori analysis of LES for droplet-laden isotropic turbulence, found that there are 5 closure terms that must be accurately predicted. And then we performed the first full a posteriori analysis of such a flow. And our mixed ANN approach uses Smagorinsky SGS stress in the carrier fluid, and it relies on neural networks at the interface to predict closure terms. We trained 5 neural networks to produce these closure term predictions, and the MANN LES model was able to closely match TKE of filtered DNS. And that's all I have. So I'd love to take some questions now, if there are any.
Thank you, Andreas. Very well done. Thank you. So we'll have a few minutes of questions from everyone, and then we'll have close the session just with the faculty and Andreas.
I'll turn off recording now in case anyone doesn't want their questions recorded.
Sounds good. Thank you.